Okay guys, this is the second part of section 1.3. This is the continuation of 1.3. And in this part, I'm going to explain to you how to find the intervals in which you can find zeros. Okay, first of all, I'm going to start with the intermediate value theorem. And what the theorem says, it says if f of x is a continuous function and a is less than b, and there is a value there's a value n such that n is between f of a and f of b, comma, then there is a number c such that a is less than c and c is less than b. And also the function of f of c is going to be equals to n. And in a graph, we can see it. For example, we have a graph that goes kind of like this and then continues. And if we have a value a here, we have a value c and a value b. And at value a, there's a value over here of y that is f of a. For c, here we're going to have a value of f of c. And for b, we're going to have a value of y that is f of b. And here, this point is going to be a, comma, f of a. Then this point here is going to be c, comma, f of c. And this point here, it's b, comma, f of b. What do I mean by that? Well, there's a corollary. Corollary is like it derives from theorems, and is also referred as the location principle. This corollary says that if f of x is a continuous function, so it has to be a continuous function, and you can find f of a and f of b, and these two y values are the same and have opposite signs, so one is positive, the other one is negative, or even if they're not exactly the same value, but if you have these two values, these two y values, but one is positive, the other one is negative, then there's going to exist at least one value c in such that the c is going to be between a and b. And if that happens, then you're going to have that the function is equal to 0. And that is, there's gonna be a 0 between a and b. Okay, so being said, So in this problem, I have determine between which consecutive integers the real zeros of f of x equals x squared minus x minus 3/4 are located on the interval. So the interval, it's -2 all the way to 2. So what we can do here is get values at -2, -1, 0, 1, and 2. And then what we do, we're going to plug in -2 into the equation. So you can do that with a calculator. And when you plug in that number into the function, you're going to have that at x is equals -2, your y value is 5.25. And then you try -1, you plug in the value in the function. And when you simplify that, that's going to be 1.25. At x is equal to 0, well, that's just -3/4, which is -0.75. At x is equals to 1, plug it in, that's -0.75. At x equals to 2 is 1.25. And when you graph that function, the graph is going to be like this. It's going to come like that. So this graph is, it supports our table that says that if f of -1, that is a positive value. F of 0, it's negative. And by the location principle, f of x has a 0 between -1 and 0 because it goes from positive to negative. And we can see that it is between -1 and 0. Now this indicates that there exists a real zero in each of these intervals. So therefore the graph of f of x supports the conclusion that there exists 1, 0 between -1 and 0. And the same thing happens. If you can see, from negative to positive, there's a change of sign. So here you're going to have another interval, and this is this one, 1 to 2. There's another interval in which you're going to have another 0. So therefore, the conclusion is going to be there are 2 zeros on the interval, and those 2 zeros exist between -1 less than x, and this is less than 0, or also we can just say between -1 and 0, and also from 1 less than x, and x is less than 2, which is the same thing as 1, 2. So you can either use the inequality notation or the interval notation. So here, these are the two ways that you can express the answer. So example number 2 says graphs that approach infinitive. So this is a third type of example. And here we need to use a graph of the function given to describe its end behavior. So we're basically focusing on end behavior. And end behavior is what happens to the function as you approach infinitive to the right, infinitive to the left. Like end behavior, what happens at the end as you move to the right, as you move to the left. And then we have to support our conjecture. The conjecture is just a conclusion. Numerically means by using a table, by using numbers. So I'm going to create a table. And on this table, I'm going to have x and y. Y, let me erase y. Let me go ahead and, instead of y, which is the same thing, let's use another notation, f of x, just like the previous example. First of all, if I analyze the graph of f of x, which is a red graph, it looks like the limit of f of x as you approach the function, the y values, towards the negative infinity, which means that towards going to the left, the function is going to go to negative infinity. And the same thing happens as I analyze the graph of the f of x, and as I move to the right, and I keep on going to the right, to the right, to the right, it seems like the graph is going to be disappears, positive infinity. So that is going to be the answer. As you move to the left, is negative infinitive. As you move to the right, is positive infinitive. But now let me go ahead and check that numerically. And I already constructed a table. As you can see, as you go to a negative 100,000, the y value is going to be negative 1 times 10 to the 9th power, which means that this has a negative 1 and then 9 zeros, which is 1 billion negative. And the same thing at x equals negative 1,000, the same thing, negative 1 million of a unit. And then at negative 100, then that's going to be negative a million. At 0 is 4. So this is going to negative infinitive. As you move to the right, then this is going to positive infinitive. So this is the numerically a way of proving that the conjecture is right. So here, my conclusion. Okay, well, the conclusion is going to be the limit. When you have to describe the end behavior, you describe it with limits. So solution would be the limit of f of x at x approaches infinitive is positive infinitive. So as you move to the positive infinitive, the graph keeps on going to the right. The second one, the limit of f of x at x approaches negative infinitive, which means moving to the left, well, the graph goes to negative infinitive. And this is the conclusion right here.